Okay, so we are on to our technical program for the morning with the theme of the end of Moore's Law or beyond Moore's Law. I like to say that the end of Moore's Law is fake news. And that's what you're going to hear about this morning. There's a notion that Moore's Law is coming to some kind of an end. It's merely a blip. Moore's Law has really represented the spectacular, explosive, exponential growth in the capabilities for information technology and information processing over the last 50, 60 years. Now, while it's true that the conventional way that we have continued to deliver the kind of increases in capabilities that enable the spectacular products and services that we all enjoy today, meaning the scaling of the dimensions of transistors, the end of Moore's Law has been predicted to occur sometime in the next 10 years, consistently going back for the last 50 years. And I think today's predictions are similarly misguided. And we're going to hear a lot about how we will continue to deliver the kinds of capabilities and increase in capabilities that really are the engine of economic growth worldwide in 4 talks today. So I'd like to call for the first talk by Professor Sayeef Salahuddin, titled The Third Era of Scaling of Computing Technologies. Just a brief introduction, Professor Salahuddin received his Bachelor's of Science in Electrical and Electronic Engineering from Bangladesh University of Engineering and Technology in 2003, and a PhD in Electrical and Computer Engineering from Purdue University in 2007. He's a co-director of the BErkeley Device Modeling Center and the Berkeley Center for Negative Capacitance Transistors. His work has focused on conceptualization and exploration of novel device physics for low-power electronic and spintronic devices, and he will give a talk today on the third era of scaling of computing technologies. So, Sayeef.
All right, so I'm going to talk about this fake news that Professor Bocker has already mentioned, the end of Moore's Law. You have it?
Yeah, do we get a copy of the slides, or do we need to scribble things down quickly?
If you want, I can send to you.
Thank you.
Yeah, no problem. Yeah, so the point I will try to make is Moore's Law has taken various phases over the years, and from our point of view, we can, at least from the hardware side, we can at least distinguish 2 different eras, and we think a third era is starting, and that's that's what I'm going to argue. So, today our life is connected. We already talked about this connectivity in terms of how our alumni has made significant contributions to this heavy connectivity that we have today. But, this connectivity comes from the power of the computers. 15.3 billion transistors are used in NVIDIA's AI chip today, and that is enabling this enormous explosion of technology that we use in our daily life. But the thing is, this is not free in terms of energy. So I wanted to look at this tweeting, where the Twitter people came and claimed that it is one of the most energy efficient method of communication. So a few years ago, they came and they said that each tweeting takes 0.02 grams of carbon dioxide emission. And their claim is every Google search, and Eric may be angry about this, but it is their claim, not mine, as every Google search is 10 times more, takes 10 times more energy.
2 orders of magnitude more value.
Maybe. I'm just looking at the energy for the moment. So to put this into context, I decided to look at someone who likes to tweet. There's no disagreement, I guess, that our president likes to tweet. And Business Insider ran this story about analyzing his tweets in the first 6 months of presidency. There were in total 920 tweets, so it is more than one tweet a day. And our president is undoubtedly popular, so each of his tweets gets retweeted almost on average by 100,000. So what I did is I calculated the carbon footprint of these tweets. And that comes out to be 1.8 metric tons. And again, to put into perspective, in 2006, an average American family had a carbon footprint of 2 metric tons per month, which actually includes all the heating, cooling, and all the other energy consumption. So what this says is that the fact that we are using technology all the time, we have to worry about their energy footprint. And this is not the news. People know about it. We are already using a meaningful portion of our total electricity use worldwide just for computing. And so there is a significant effort trying to increase the energy efficiency of the computing technology. And so the question is, what can we do from the hardware side to approach this problem? So again, if we look at the history of the computing technologies themselves, we already mentioned this 15.3 billion transistors being used in NVIDIA's AI chip. This humongous integration has been possible by what we call scaling. And the way we look at it, that there was an era of geometric scaling where basically we were trying to solve all the problems related to scaling down the dimensions of the devices. That pure geometric scaling has gone away long time ago. In the last 15 years or so, the way scaling has approached, yes, they are scaling the dimensions, but there are other things came in which we can call effective scaling. It's my name, so if you don't agree with it, that's fine. But the point is that the way that era has progressed, and we are actually in the middle of that era, is where people have strained the channel to increase mobility so that the current goes up. People have gone to high-K metal gate so that the charge goes up, right? It's not directly coming from the scaling of the dimensions. And of course, from Berkeley, Professor Chen Ming Hu is right here, the FinFET came along where you basically took the channel of the transistor and rotated it by 90 degrees so that the width of the transistor came on the third dimension and you get more current per footprint area. So we call this effective scaling. So what I argue is that yes, people are again talking about how these technologies may run out of steam in the next 15 years or so, but there is a third era of scaling starting, which will be enabled by transistors which work completely following a completely new physical principle, by embedded non-volatile memory that people are looking at in different types of materials, in different types of architecture, and trying to put these things together in 3 dimensions, which is not possible today. Okay? So we recently were awarded a center grant as a part of a big initiative from DARPA and SRC to pursue this vision. Again, this center is going to look into these new types of transistors, new types of non-volatile memory, how to connect them in monolithic 3D fashion, and also how do you connect different types of technologies made by different foundries on the same fabric. Okay, so it's basically trying to do an app version for the hardware. Can you take chips from various people and put them together on the same fabric? So this is a center that we call Ascent. The director, the center is Suman Datta from University of Notre Dame. I'm an associate director of the center. It has 13 universities and right now 20 principal investigators. So I just wanted to mention that this initiative from DARPA and SRC is being called JUMP, and they have in total 6 centers. And Berkeley ECS faculty are co-leading 3 of them. So we have a reasonable footprint in that initiative. But coming back to the kind of technologies that we are looking at. So for example, very recently, we have shown that using magnetic tunneling junctions, which has just recently been announced as a technology that you can design with in TSMC foundry process or Global Foundries foundry process, we showed that you can build up circuitry where the logic can flow in the opposite direction. So usually, if you think about a NAND gate, I take 2 inputs, I get 1 output. But we can build up technologies, again, based on something that is manufacturable today, where if you actually set the output of the NAND gate, you can get back the input. And this reverse flow of logic, one can show that it can solve then stochastic Boltzmann machines, which are being looked at for artificial intelligence today. So, this is one of these exploratory things that we are doing, but we believe that this is already manufacturable. In fact, we are talking to at least one foundry to see if we can get a tape out of this reverse logic function. But one of the other technologies, new technologies that we are looking at, and I'm going to spend some time today talking about this, is this integration of ferroelectric materials. So integrating ferroelectric materials with transistors to give us memory is a 60-year-old idea. Okay, a long time, actually in the 1950s, Bell Lab scientists and IBM scientists already talked about it. We were never able to do this very well, so there is a very niche market of ferroelectric memory today simply because we could not integrate ferroelectric materials with silicon. This changed around a few years ago, where it was found that hafnium dioxide, which is used in the transistors already, can be made to be ferroelectric. And so this is one of the results from our own group, which shows this hysteresis, so charge versus voltage. Because you can get 2 different states at the same voltage, you can use it as a memory. And so what I'm showing here is a transistor that was made at Berkeley, which shows these 2 different states in the IDVG already. There is a 6 orders of magnitude on-off ratio. And this is integrated on a high-performance transistor already. This is something that could not be done before. So this is one of the technologies that we are actually looking at for embedded non-volatile memory. Okay? But let me go back to the lowest level, which is the transistors. Actually, before that, one of the other things that we are pursuing also in this context is that if I can get this memory, the oxide that is needed to give me this memory is actually compatible with the backend. So in principle, I can create polysilicon transistors, vertical transistors like this, and put that oxide on the sidewall, get a vertical transistor, and get a CAM cell, content and addressable memory cell, just by putting 2 transistors together. So these CAM cells are used in enterprise servers because they allow you to do parallel search. But right now, they're made of SRAM cells. It takes 14 transistors in total to make 1 CAM cell, and it's not non-volatile. This is a non-volatile technology. Going even into this exploratory path, a CAM cell gives you an XNOR function. And if you actually think about it, these guys can be connected together in various ways to give you NAND, NOR, and other functions. So in principle, if you can actually store your bits, you don't have to write to them anymore, but you can do logic functions. It won't be very high performance because it's not complementary, but it is still can perform digital logic. That's what we see. And so this may be a way of actually building up logic in the 3rd dimension. So we are looking into these possibilities. But coming back to this lowest layer, as I said about the transistors, so the point is that if we look at the transistors, we are flowing a current from one side to the other. And if we want to work at a certain speed, that is proportional to the current that is going through that transistor. So as a result, if I'm trying to look into an energy efficient technology, I need to reduce the voltage, but the current is already fixed by the speed at which I want to work with. So the only way to reduce the voltage will be to get a current voltage characteristic which looks like that. Rather than this, I want something like that. Okay? So the question is, why can't I make a device which just gives me that. What is the problem? So it turns out that that problem has a very fundamental origin. So this is a tombstone of Ludwig Boltzmann, and inscribed in it, actually, in fact, in his tombstone, is this equation, which sounded interesting to me. But remember that Boltzmann committed suicide because people say that he was frustrated, that his idea, which was very controversial at that time, but today is well accepted, that entropy, which is given by this equation, is always increasing. So people at that time could not believe that universe does not want order. Universe wants disorder. Okay, why is this connected to computing? Because if we are doing computing, we need to put things into order. So we need to act against the universe, which means we need to spend some energy. And that energy is proportional to the change in the entropy. So if you are working with a digital computer, 1 and 0, and you are working with n electrons, the total disorder you can create in the system is 2 to the power n. So that energy becomes proportional to this degree of freedom. So in a transistor, this actually comes in, this statistic comes in very beautifully in the way the electrons are distributed at the source. And when I run a transistor, I apply a voltage at the gate, I bring down this barrier so the electrons can flow, but they can only flow in the way they are distributed at the source according to that Boltzmann statistics. And as a result, this current cannot go up arbitrarily sharply because it is limited by that statistics. And it turns out that if I want to change the current by one order of magnitude, I need at least 60 millivolt. So this has been called the Boltzmann Tyranny. Often people call it Boltzmann's curse, that we have a limit. If I fix my current, I cannot reduce my voltage arbitrarily. Okay? So this looks very fundamental, and what can we do about it? So we basically said, this is when I was still a PhD student, is that we should start with materials that has already gotten some energy from nature and has gone into an ordered state already. So one example is these kids. So let's say that we are doing an exercise with the kids. They can only stand up or sit down. So there are 1, 2, 3, 4, 5, 6, 7 kids. So if they are allowed to do anything that they want, stand or sit down, there are 2 to the power 7 ways you can arrange them. But now if I introduce this restriction that they all have to hold their hands, now there are just 2 ways. They can all stand up or all sit down. So what has happened is we have reduced that order, reduced that entropy from 2 to the power n to 2. So suddenly the factor of n goes away. Okay? And of course, to hold hands like this, they have to spend some energy, and this energy they have to take from something. Maybe they have eaten in the morning. That's the energy they're spending. So turns out that in nature, there are materials which have already stored energy in themselves. We call them phase transition materials. They have gone through a phase transition. They have stored some energy in themselves. So one of them is the ferroelectric materials. They have these dipoles. They are arranged together, and they can be either up or down. So even if you have n dipoles, rather than 2 to the power n, your total degree of freedom is just 2 in the ideal case. And so we made this proposal that if you can use them as the insulator material on a transistor, your total power should go down below what Boltzmann's limit says, right? And it turns out again that this fact that you have a ferroelectric material, it has a stored energy, it turns out that it comes out in the material as a manifestation of a capacitance that is negative. So this is a standard insulator. We all know a parabola chi square over twice c gives me a parabola. At 0 charge, I have 0 energy. That's fine. But if I want to store some energy at 0 charge, I need to push it up. And as I push it up, the curvature of this curve gets reversed, and I get a negative capacitance. So this idea that you can put a ferroelectric material on top of a transistor and reduce energy below Boltzmann limit, we called it a negative capacitance transistor at that time back in 2008. Now, of course, if you are fresh out of graduate school and you claim that you can break a limit that has Boltzmann name associated with it. Some people get very upset. So, but Berkeley is a fantastic place. I came here in 2008 as an assistant professor, and my senior said, go for it. So I actually remember a discussion with Professor Chen-Ming Hu at that time, sitting right there. He said, if you believe in it, go for it. So we went for it. Took us a long time. But this was the first experimental demonstration that actually created a lot of interest in IDM 2015. This is a collaborative work with Professor Hu's group, where we actually did this FinFET, which is the standard technology today, at a 30 nanometer channel length. And this is the baseline transistor, and you see the negative capacitance transistor actually steepens the curve, exactly what the goal with which we started. When we looked at this slope, which means do you need 60 millivolt to increase current by 1 order of magnitude, we actually saw that that limit has also been reduced. Okay, so this was, started some interest. In fact, after this, we also started a center here that we call the Berkeley Center for Negative Capacitance Transistors. So this is one of our most recent results. In FinFETs, as we said, that we have rotated the channel by 90 degrees. But what happens is, as you go down in the node from 22 to 14 to 10, the aspect ratio of these fins will have to go up to keep the benefit properly. And this aspect ratio going up is one of the biggest scaling challenges. When people say we cannot scale it down, one of the reasons is this, because you cannot keep increasing the aspect ratio. At some point, the fins will break down. So what we have shown recently is that if you look at a conventional transistor, yes, the SS is that slope. It gets worse and worse and worse as you reduce the aspect ratio. But when you look at the negative capacitance transistors, it actually holds on to that aspect ratio. So we believe because of this, it will help the scaling way out than what is now believed to be the limit of the FinFET scaling, just because of this, because we can work with a lower aspect ratio. Now, this is not, these results are all, these transistors are made at Berkeley, but recently we have had a breakthrough. Actually, Global Foundries demonstrated a negative capacitance transistor in their 14 nanometer FinFET process. So what I'm showing here is an interesting plot. It is the current of the negative capacitance transistor divided by the current of the product that they sell today. Okay? And of course, they don't want to show you the exact current, so it is a ratio. But what you see is at smaller voltage, that ratio is way less than 1. In fact, right here, it is around 0.1, so it's almost 10x lower. But as you increase the gate voltage, that ratio goes above 1. So at around 1.2 volt, it is around 1.8. So what it is showing is that the negative capacitance transistor is giving you lower off current, but higher on current for the same voltage window. So that is exactly what we are looking for. So this is the output characteristic of their transistor. If you look at this dashed line, this is again their 14 nanometer product that we use today. Again, the NVIDIA AI chips made of 14 nanometer FinFET transistors. This is that line. The solid lines are negative capacitance transistors. Again, you see almost a 2x increase in the current for the same voltage. So Elad is going to talk about analog design. So we looked at these Global Foundries transistors and looked at some of the analog parameters. You see that GM goes up. GM is the transconductance. It goes up. The output resistance goes down. So the total amplifier gain actually increases. And in their 40 nanometer transistor, it increases almost by 4x. So that's kind of interesting for analog design. The breakdown voltage also increases simply because of what we said, that for the same aspect ratio, you get a better behavior. So it acts against what is called the short channel effect, which is one of the things that limits the scaling. Okay. So we did some calculations as to what kind of energy, yes?
Yeah, I mean, what kind of frequency
Q, I don't know. What we know about is that the ring oscillator frequencies, and we have seen them going up to 7.2 picoseconds so far in this node. So this is completely determined on what the foundry will give us. So right now we don't see any frequency limitation of this until you probably reach 500 femtosecond, where you basically start to approach the atomic vibration of the hafnium atoms in the system.
Well, I'm looking for some kind of CV curve over frequency.
Oh, so from say 100 kilohertz to 10 megahertz, nothing changes. Beyond that, again, measuring capacitance becomes difficult for us. So the standard digital characterization shows no difference. That's the thing. So again, going back to our energy calculation, what we find is by steepening this curve like this, for the same delay of the speed of the circuit, the energy could go down almost by 10x. Again, hopefully that is a big boost for the energy efficiency in the circuits. And so yes, so we are very confident now to say that the Boltzmann curves, which has been known for many decades on conventional transistors, that has been lifted now. Okay, and coming back to this point of third era, I gave you example of a logic transistor which acts on a physical principle that is completely different from the conventional. It looks like a transistor, but actually the physics is very different. And there are other devices that are being looked at. These devices in the logic side, in conjunction with the advances being made in the embedded non-volatile memory, and hopefully ways to put them in 3D, we believe that will enable this third era of scaling and a non-linear reduction, improvement in energy efficiency. So I'll stop.
Fake news is always controversial. I'm sure we have some questions or comments. Any questions? Yeah.
Yes.
I mean, right now, I don't know if you need a faster FET rather than a faster interconnect. I don't know the limitations is for a faster device is what we're crying for as much as filling the interconnect power, which is what's limiting as not going from beyond 4 gigahertz, of course, right now.
So here is the way I look at this problem. I agree with you in general. So we are looking at that, can you get the same on current at a lower voltage? So let's say keep the speed the same and you can run it with lower voltage. Your interconnect energy efficiency goes as CV squared. And when you are driving the interconnect, that C is the main C. So if your V goes down by X, your total energy will go down by X squared. So the question is that, can I run the transistor at a smaller voltage for the same speed? That's the question. Now, there are people who are interested to run I/O devices at way faster speed because they want to communicate, and there they are not really worried about the voltage. This guy can also give you that. You crank up the voltage, you get 2x the on current. But I'm saying that at the same on current, your voltage is smaller. So the interconnect energy dissipation should also be smaller.
Any other questions? All right, let's thank Sayeef for
Thank you.